Welcome all to week 8 tutorial for the course Introduction to Machine Learning taught by Professor Sudeshna Sarkar. This week, the topics that I am planning to cover is some techniques in unsupervised machine learning and clustering I'll cover in detail. Okay. So if you have any doubts, you can unmute yourself anytime and ask, or you can also type it in the chat box. It's up to you. I'm Pintu Kumar and I'm a PhD scholar at IURIT Bombay. Okay. Let's start. So, during this course, you might have came across many machine learning algorithms. Some of them were supervised, some of them were unsupervised. So, most of the focus was on the supervised part where you had some data point xi along with its label yi. Okay. Now, in unsupervised learning, you don't have your labels available with you. You just have the data points, and the label is so based on the pattern of the data, you want to infer something about the data. Okay. So, for example, if you consider probably think about when human civilization would be developing, at that time they didn't knew anything about the world around them. They didn't had any person to tell what is the label that this is a dog, this is a cat. They bifurcated them like different animals into different category and then they named them something. So the idea of unsupervised learning is something similar, that you want to learn from features of the data points rather than labels. Okay. So some of the common unsupervised learning tasks are, first is your dimensionality reduction. So if you have, let's say, some data point in 100 dimension, you you want to reduce the dimension of your data points to something smaller so that it is easy to manipulate or do around with. So let's say you want to reduce this to something of dimension 10. Okay. So like how does this reduction in dimension help? First is you can better visualize this data if you are in lower dimension. Let's say your original data is in 10 dimension, and if you are able to reduce it to 2 dimension, then or 3 dimension, then you can visualize this thing and you can infer something about the data using your own wisdom and intelligence. Second thing is that it requires low memory for to process the data. Also, it helps you sometime overcome this curse of dimensionality and those kind of things. Some of the common techniques that is used for dimensionality reduction is your principal component analysis and autoencoders. So both of these techniques have been covered in the lecture course at some points. I'm just sort of mentioning it right now. Okay. Next like thing is something called anomaly reduction. So let's say you have a data point in 2 dimensions and your data point is something like this. Okay. And you have a data point here, and then you probably have something starting from something starting from here. So if you look at this data, then this kind of very clearly forms 2 clusters of data. But this point sort of is anomalous or like erroneous data that has came in. So we want to detect this kind of data and want to remove these kind of things. So we want to remove the outliers in the data. Okay. So this is the idea behind anomaly detection. This is also an unsupervised learning technique. Third and quite useful these days is a technique called embedding. Okay. So if you have whatever techniques you have learned till now, I'll just use some space here. Sorry. Okay. So if you recall whatever you did in this course, what was happening was like you were given with some data points, let's say x1, x2, Some places you had your labels along with you, some places you didn't had your labels along with you, but you have some data points. Where did this data point belong to? These xi generally belong to some Rn space. So all these values were some vectors. So in some R cross R cross R. So what was your task? Your task was to learn a function f so that if you input something to it, it can give you a proper output. Okay. Now, if you look at many applications of this machine learning and deep learning in your day-to-day life, some of them would be something like Google Translator. Okay. Or like you can be uh, something like your uh, uh, estimate time of arrival on Google Map. Okay. So if you look at this kind of application, one thing that you should notice is, like if you look at Google Translator, what it does is it takes a sentence in one language. Let's say it takes sentence in Hindi, then it can output you a sentence in English. Okay. But whatever we learned till now, all those techniques, most of those techniques kind of took like your numerical values as an input and outputted numerical values. Then how to deal with these kind of situations? Like how to deal that words are getting as input or words are being like given as output. How to deal with those kind of situation? So to deal with those kind of situation, what we like look forward to is something called embeddings. So what we try to do is like what whatever data set we are working with. So if we are working with, let's say, words, then we want these words to be converted into some vectors and then apply some machine learning algorithm on top of it, get the output, and then convert it back to our desired data type. Okay. So this process of converting, let's say, word to vector, like or any other data form to vectors, is called embedding. Okay. So in embedding, what you do is you convert your desired data types into vectors. So for example, like in some initial, like I think week 0 tutorial, there was something called bag of words. Okay. So there what you did is like you converted a sentence to some vector. I am just mentioning it because this is being used very much these days in area of research as well as in application. So I thought I would just mention it at least so that you know like something like this exists. Okay. So if we look at some of the traditional method to uh, do embedding is, so these methods can be your something called bag of words that I mentioned for your texts or like you might have seen there are data types of this type. So this is something called graph if you look at it mathematically. So these are your nodes and there are some edges between these nodes. So in real life, like many real life data exist in form of graphs. Okay. And like in many applications, you can convert your data into graphs. So like machine learning or graph is a very useful tool to have. So for those kind of embeddings, we like look towards factorization of matrix in specific factorizations of adjacency matrix or like your factorization of other similarity that you obtain from your graph. So something like Laplacian matrix or those kind of things you can factorize to get your embedding out of it. How to do is like sort of out, not in the scope of this course because this is an introductory course, but yeah, just to mention. After this, like initial techniques in year around something 2008 to probably 2015, 16, some of the techniques that came in were like word to vec for words, node to vec and deep walk for graphs. So these techniques are based on something called random walk based approaches. So you generate these embeddings out of a technique called random walk. So this is also just to mention. And if you look at the more recent or the techniques that are being used these days, so for words, this list includes transformers or BERTs. So this is bidirectional transformers. So these are very common these days, and something in graph setup can be GCN or GNN. So this graph setup also helped in many drug discovery recently. And this AlphaFold 2, some of you might have heard. This is to predict a 3D structure of protein. So these techniques were used over there also. This was very popular recently. So these are like how embedding works. So anything you have to ask till now? Otherwise, I'll proceed further.
Technology called cyber used in bioengineering. Which of these embeddings is used in it?
Can you please repeat?
Third, name this one technology called as cyber used in bioengineering.
Diksha, I think your voice is not very clear. Can you type it in the chat box? I'll try to answer.
Sir, am I audible now?
You are.
And there's one technology called as cyber used in bioengineering.
Okay.
So which kind of embedding is used in it? If you are aware about it?
I'm not aware about the technique we are talking in this biotechnology. Sorry, I won't be able to answer that.
Okay. Thank you, sir.
Jatin, can you please turn off your mic? So I'm not very sure like what kind of data set do you guys encounter over there. But yeah, so that's why I won't be able to answer. But the basic idea for these embeddings is like you have something called original space, and you have something called embedding space. Okay. So like if you look at original space, this is your set of words, or in graph setup, set of nodes. And in embedding space, you will get some vectors. So you want to reach from here to here. So the basic idea is that you want, like if two words are similar over here, then their vector should also be similar in the embedding space. This is your basic idea, like that most of the embedding techniques follow. And your different embedding techniques, they just vary in sense of what similar, like definition of similarity you are using over here and what definition of similarity you are using over here. Okay, so I'm not very sure like what kind of data set you have in like that biotechnology application that you're saying, but like this is the basic framework. If I would like, you can post it in the forum, like whatever details are, then I can probably tell you something more about that. So now we move to like what was covered in the last lecture, that is your clustering. So clustering is also an unsupervised technique of machine learning. So in clustering, you have your data points available with you, just the features, and then you want to group them into different different clusters. Okay. So if you look at this data set over here, this is in 2 dimension. So you can see that this points that I'm drawing with a purple thing forms one cluster, this thing that I've highlighted with green, and the other one in the down forms another cluster. Okay. So we want machine learning to like we using our wisdom were able to directly infer that there are two separate class of data points, but we want a machine learning algorithm to infer this thing. Okay. So what we want is points that are within a cluster should be close to each other. So we don't want that, let's say these are 4 data points. So we want these, like if points are close to each other, we want them to be in a group rather than we considering all the elements in a like group. So yeah. So one of the common technique to do this is your k-means clustering. Okay. Now in this k-means clustering, this k denotes your number of clusters. Okay. So this number of cluster you have to fix a priori. So this is sort of a hyperparameter you can say. Okay. So you have to fix this k before you start doing any kind of computation or anything. So like this k means clustering can be summarized into three or four broad steps. So first of all is you have to like initialize like a central point for every cluster. So you initialize that you wanted to have k clusters. Now the first step is to initialize some random center points for all of these clusters. Okay. So let's say this is your plane. So you assign that this point is my cluster 1, this point is my cluster 2, this point is my cluster 3. Okay. Now in next step, you look at all the points. So let's say what points are close to point 1 will be assigned to cluster 1. Whatever points are close to cluster 2 will be assigned to cluster 2. Okay. So this is how we proceed. So let's say you have some data point xi. What you look at, you compute its distance from all these things. So you compute its distance from mu1, you compute a distance from mu2 and so on. And then you look at the, then you pick the k which had a minimum distance from xi. So, and you assign xi to that specific cluster. Okay. So this is how we do. So like you want to find the minimum distance between xi and mu k, and you want to pick the k which had this minimum distance. So how do you choose upon this distance, or what is this distance? You can pick from variety of distances based upon your like nature of data set and those kind of things. So some of the common ones are your Euclidean distance. So like your Euclidean distance is nothing. So I'll just mention what Euclidean distance is. Somebody if is not from probably some mathematics background. So if you have x and y, then the distance between x and y is x1 minus y1 whole square plus x2 minus y2 whole square, and so on till xn minus yn whole square, and then you take the under root of it. So this is something called your Euclidean distance. Another generalization of this Euclidean distance is something called Minkowski distance. So rather than taking your this square term over here, you can take any power p. Okay, you can take any power p, then you sum it up from I is equal to 1 to n, let's say. Okay, and because we replace this 2 by p, so we will replace this 1 by 2, this square root, this 1 by 2 also by 1 by p. So this is a generalization of your Euclidean distance. This is called Minkowski's distance. Okay. And last one, but a very important one, is cosine similarity. So this is not a distance, but a similarity measure. So you can transform it to distance, obviously. So your similarity between x and y is x dot y by norm of x into norm of y. Okay. So this kind of captures the notion of angle with it. So if two vectors have less angle between them, then they will be close to each other. Now getting back to our clustering thing, what we did was we assigned some random central points to each cluster. Then in the first round, what we did is we looked at every data point, we computed its distance to every of these center points, and then we picked or assigned this point to a cluster from whose center point it had least distance. Okay. Now in step 3, what we will do is we will recompute this mu I, or the center points. How would we recompute? We would just take an average of these xi's, whatever have been assigned to that like cluster. Okay. Now we will repeat this step 2 and 3 till the time until this thing converges. Okay. So when do we say that this thing has converged? Like there are 2 or 3 criteria that you can decide upon that this thing has converged. Like if in 2 consecutive steps, if there is no change in this mu I, then you can say that this thing has converged. Okay. So another thing is that if your like assignment of data points does not change. So like if you updated your thing, even then like the data points, how the way they were assigned earlier to whatever cluster, they are sticking it to their like assignment. then also you can stop doing this thing. Third thing is there can be situation like when there is large number of data points and data points are not very cleanly getting separated. Then what you can do is like you can compute a quantity called within cluster sum of square.
Sorry to interrupt, Pintu Kumar.
You can. Yeah.
Uh, Please tell us the today's agenda, what we are discussing now.
Okay, so like today's agenda is based on your like last week's lecture, whatever we did. So clustering was the main focus in the last week that Professor Sudeshna sir taught. So I sort of have till now have talked about some of the unsupervised learning methods that are related to clustering, because clustering is an important unsupervised method. So I thought about covering some of the methods that were not covered in the course or were related to this. And now I'm covering this clustering in
K-means
detail.
cluster. Okay.
Okay.
Go on. Thank you.
Yeah. So now when we look at this within cluster sum of square distance, okay. So how do we calculate this is like what we do is like if whatever points are there in one cluster. So let's say we had these points, these clusters. Okay, there were two clusters that we formed. So we look at the distance between this and this points. So we look at distance between this and this point. Then we look at this and this point, and then we sum these distances and we keep accumulating this. So this is called within cluster sum of square. So across cluster we'll sum it up. And this quantity, if this thing, there is very less change in this within cluster sum of square thing, then also you can stop doing your k-means like repetitive steps. Okay. Like if it is not very clear, I have prepared a dummy example for you so that it is very clear to you, like how k-means clustering works. So here is an example. Consider like there are only 4 points in the data set. That is not practical, but yeah, for the time being considered that there are 4 points. So I have marked this over here also. You can look what these points are. So let's say we have 4 points over with us, and this k we want to fix 2. So as I mentioned that k you have to fix on your own, like what k you want to choose. So looking at the data, I'm choosing k is equal to 2. You may choose k is equal to 3, or somebody else might have some other opinion. That depends on like the underlying application, whatever you're doing also. Okay. And then what was our first step? First step was to assign some random mu1 to mu n, mu k, right? So now because we have only two clusters with us, let's assign two random mu1 and mu2. So one thing is that I have picked this mu1 and mu2 from the list of data points only. You can take any point in this on this like 2D plane. You could have picked this point as mu1 and this point as mu2, or somebody would have picked this point as mu1 and this point as mu2. And based on your initial choice, how you're picking up mu1 and mu2, your final clustering might vary. Okay. So for the example that I'm mentioning, so I have picked this mu1 to be your A, okay, and mu2 to be B. Just for simplicity, I picked the top 2 points. Okay. And the distance that I'm using over here is your Euclidean distance. So this 2 bars norm with a 2 subscript is something called Euclidean distance. So this is your, as I mentioned, x1 minus y1 whole square plus x2 minus y2 whole square and under root of this. Okay. So now if you look at, we'll try to calculate the, let's look at the first data point A. Okay. And we try to find this distance from mu1. Because these 2 points were same, so we had distance to be 0. Now let's see its distance from mu2. So it is 6 minus uh, 6 minus 2 square, this is 16, plus 1 minus 3 square, which is your 4. So it would come out to be square root of 20. Now compare these two values, which one is lesser? Obviously your first one is lesser. So we assign this data point A to cluster 1. Okay. Now if you look at this, these red points are over here your cluster 1 and the blue points are your cluster 2 in this figure. So I have assigned A to cluster 1. Okay. Now let's come to B. Okay, B, because again, this B we have chosen as mu2. So its distance with mu2 would be 0 and it would be non-zero for some other point. So I have skipped the calculation over here. So assign B to cluster B or cluster 2. So I have assigned this B to the blue point or the cluster 2. Now let's look at C. Okay. For C, C is 1 comma 2. Okay. We take its distance with 2 comma 3. So it is 1 minus 2 square, which is your like 1. Okay. And then you sum it up with like 2 minus 1. This is also 1. So you get root 2. And with mu2 again, you get something like root 20. Okay. So which one is lesser? Obviously root 2 is lesser. So we assign C to cluster 1. Similarly, we assign D to cluster. Okay, now in D, what we got is from both the points mu1 and mu2, we had same value of distance, that is 10. Okay. So in such kind of situation, you can randomly assign it to one of them. Okay, like you need not worry much about these kind of situation. You can simply assign randomly to one of them. Okay. So I assigned it to 2 randomly. Okay. So D I assigned to 2. Okay. So this is my first epoch. So after one run of this algorithm, I have got this clustering that C and A are from like your first, wait, yeah. C and A are from your first like cluster and D and B are from second cluster. Now as per the like step 3, what we need to do is we need to reevaluate our mu1 and mu2. Okay. How do we reevaluate? We take a average of all the data points belonging to that cluster. So here I have taken C plus A, and how many points we have? We have 2, so I have divided by 2. So 1 plus 2, 3 by 2, 3 plus 2, 5 by 2. So your this point over here, so this is 3 by 2 is this, and yeah, this point would become your mu1 updated after one step. And similarly for the second one, your I think this is 4.5. So this is your 4.5 and 0.5. This one becomes your updated mu2. Okay. Now we need to repeat the same steps again. So here are the distance that I've already calculated. So you can try calculating it. You would also get the same answer. Okay. So the distance between A from mu1 and mu2, both these things I have calculated. So what I got is that its distance from 1 was lesser. So I assigned it to this cluster 1. And for B, I assigned it to clusters 2, C again to 1, D again to 2. This time we didn't had same similarity for case D. This time it was different. So if you look that we got again the same cluster. So this point is A, and then we got 2 over here and 2 over here. So we again got the same cluster. So because we got the same cluster again, we can stop running our algorithm over here. Okay. So this is how your k-means clustering work. Okay. Now, before I ask you about your doubts, one more thing just to mention is how do you decide upon number of clusters? I said that it's upon your wisdom, you have to choose a priori. But if you are not getting any information from your underlying task, like whatever you are trying to do, wherever you are trying to apply this, you don't have any idea upon how to decide upon the number of cluster, then what to do in such kind of situation. Then what you can do is, like there are many methods, but one of the very common one is something called elbow method. Okay. So what you can do is, like this is the number of clusters on x-axis, and this is sum of squared error. So this is within cluster sum of squared error that I mentioned just before this. So you started with one cluster and then you found the optimal cluster for like k is equal to 1, you ran k-means clustering and then you found a clustering. Okay. And you like for the final clustering that you obtain, then you find out it's within cluster sum of square error. So you got something over here. Okay. Now for 2, you again found the same thing. You ran your k-means clustering, you reached an optimal point. On that optimal point, you found the sum of squared errors. Okay. Again for 3 and so on, you can run for some like whatever range you are hoping that your number of clusters would fall into, you can run for that. Now there will be a place you will see an elbow kind of structure. So if you look at your elbow, at one point it kind of have a like obtuse angle kind of a thing. So here you can see at k is equal to 3, you have some elbow structure. So this, whatever I'm drawing, this example, this is not for the example that I just mentioned before. I have just randomly picked this image. So for that specific data at this 3, you can see there is an elbow kind of structure. So we will pick 3 as our number of clusters. Okay. So this is something called elbow method to decide upon the number of clusters. Now, like I'm done with k-means clustering. Any doubt on this k-means clustering? Okay. Let's look at some of the questions that were like, if nobody has doubt, I think you guys will, I'll expect you to answer these questions. So, yeah. So, it is asking is, in which of these cases will k-means clustering fail to give good results? Okay. So, let's go one by one. Like if data points has outlier, what would happen? Like would your k-means clustering give good results or not? So, like what is your guess? Like would it give or would it not give? So when you have like some outliers, okay, let's say this point is an outlier, okay, and these points are very tightly packed. So what this point will do is, this point will cause like issue when you calculate, like let's say you assign this to cluster 1, because this point is outlier, this will shift your mean towards itself. Okay, so this thing will cause problem. First is this. Second thing is, like let's say this point is in middle of this. Okay, then where to assign this kind of thing kinds of become very difficult. So yeah, so k-means clustering don't give very good results when your where your data points have outliers. Okay. Uh, So first one is fail to give good results. So first one would be correct. So second is when the data points is in round shape. Now, like if you look that this your k-means clustering sort of finds distance between each and every point, and that distance is very useful. So circle is a shape. Like if you arrange data points in a circular shape, then you are able to minimize the distance between each and every like every pair of points. So circle is a sort of very good kind of a set for this k-means clustering. So second option is not correct. Okay, so third point is the data point is a non-convex in shape. Let's say your data point is something like this. Okay. So these are your one type of data points, and your another point type of data points is something like this. Okay. Now if you are relying upon your k-means clustering, then look at this. So the distance between this point and this point is less, and this point in this point is large, right? So what would k-means or like suggest you, like if you have this as your center for this outer data set, then also this point is nearer than this point. So this kind of situation also your k-means clustering would fail. Okay. Okay, if your data points have different densities, again, same thing would happen. If your like one data point is very tightly packed, another one is sort of very spread out, then again this thing is susceptible to fail. Okay. Let's move to the next question. So this was asked last year probably, I guess. So assume that you want to cluster 7 observations, okay, into 3 clusters, okay, with k-means clustering algorithm. First iteration of the cluster is this. Okay, so you have your first cluster as this, second cluster as this, and third cluster as this. What would be the cluster's centroid? Sandeep sir, can you mute yourself, please? Yeah. So, like anyone wants to attempt this, can you please type it in the chat box? So we are given with clusters and we want to find the cluster centroids or the your mu1, mu2, mu3 that I mentioned in my notation. So you want to find the mu1 for this cluster, mu2 for this cluster, and mu3 for the third one. Can you please tell me what values you are getting? So you need, like, let's say for C1, what you need to do is there are 3 data points. So 1 by 3, 1 plus 4 plus 7. And second position is also 1 plus 4 plus 7. What would you get?
Is it first one? A?
Yeah, this is first one. Yeah. So you just need to sum this up and divide it by 3. So it is 12 by 3 and 12 by 3. So this is 4, 4. You can do similar thing for the rest 2 parts also. Okay. Now it is asking is, let's say following from question 5. So question 5 is whatever you saw. What will be the Manhattan distance for the observation 9, 9? Okay, 9, 9 from your centroid C1. Okay. So I'll just mention what Manhattan distance is. Your Manhattan distance is your 1 min cos k distance, or it is given by, let's say you have 2 data points, x and y. Then the min cos k distance between x and y is x1 minus y1 mod plus x2 minus y2 mod. Okay. So you need not take under root or anything. You just take the difference of the first position, take their mod, and then add it to the difference of second position. Take like again with the mod. So it is asking you like from like this centroid of C1. What is your centroid for C1? It is 4, 4. What is its Manhattan distance to the point 9, 9? What it would be? 4, 9 plus 4. I think this should be easy. 5 plus 5, it is 10. So your A option is correct. Okay, any doubt in K means then we can move to hierarchical methods.
Sir, I have one doubt.
Yes, sir.
Sir, actually, elbow method you discussed, right? Other than elbow method, what are the points to decide the K? K.
So again, like, so there are methods. See, if you look at this figure, what is happening over here is, if you are increasing the number of clusters, there is not much increase in like your like not much improvement in your whatever like quantity that you are using over here. This can be your sum of squared, or you can come up with some interesting ideas like whatever thing you want on your y-axis. So with respect to that, when you have like very less decrease in this points, so with increase in cluster, you are not getting much out of it. Okay, you are redundantly increasing your clusters. So in for so to decide upon that kind of situation, one method is your elbow method, and you can again choose this like you can fix some, let's say range, let's say some value, let's say 10 to the power -1 you chose, and you said that if my decrease in this value, whatever this is, let's say within cluster sum of squared, okay. So if this is like not more than this, then I'll stop. So one criteria can be this. And again, this might vary from your like area to area. Let's say you are like you are working on some problem where you know that your uh, every clusters have like more than 10 elements, or let's say less than 5 elements. You have a priori knowledge about that. Then you will not use this elbow method there. Okay. Then what you will do is you will stop when every cluster has less than 5 element, or you will stop bifurcating further when you have more than 10 elements. So this depends on area to like whatever problem you're working, but a common, like when you don't have anything, you can use this elbow method.
What is Silhouette coefficient?
I also saw that in the like questions, I guess, but I don't think that was covered in the class, and I'm also not aware of it. So I'll probably inform Professor Sudesna Sarkar about this, but I'm not very sure what it is.
Kumar sir, actually
Huh.
my question was, other than elbow method, what are the other methods to decide the number of clusters? That was my question
Huh,
actually.
that's
I
what
have understood elbow method.
that's what I told you. So like elbow method is just one technique. Uh, so I won't name any method, but what I'm saying is like what is the basic idea behind elbow method? So this elbow method is based on an idea that beyond this point, the decrease in this sum of square is not very large. So you can come up with a method so that you can guarantee this thing. So that would be another method that you have to do. And this elbow point we decided for a like when we didn't knew anything. But if you have any more information, you can like decide on other points also. So the idea would remain universal that beyond a certain point, if there this decrease is very less, then you will won't go for those kind of like that number of clusters. That idea would remain universal side. So okay,
The questions again, please, sir. I lost my internet connection. Sorry to say.
okay. What I was saying is, so what the basic idea
Questions. Which questions
question?
I was asking?
Which question?
Discuss, na? You discussed the questions, na? Just few
Mm-hmm.
couple of minutes back.
So what questions you have doubt in?
Just, sir, please go through it quickly so that.
Okay. See, so the first question is asking in what kind of situation your k-means clustering don't perform very well. Okay. So like if you have data points with outlier, what I mentioned is then your k-means clustering won't perform very good. If your data point is in round shape, then actually k-means clustering perform very well. Okay. If your all the data points are in circle, then it is very easy for k-means cluster to like separate these clusters. Again, if your data points is in non-convex shape, I gave this example. Okay. So if you have this red and blue clusters, probably your average for this blue one would lie something over here. So if you look at the distance between these 2 points and these 2 points, this one appears to be larger. Okay. So in this kind of situation also your k-means clustering don't perform very well. Another one is if your data points have different densities, then also it won't perform. Okay. So first one was this. Second one, I think it was easy one. So you are given some clusters. Okay. And then this C2 and C3, then you have to decide upon this cluster centroids. Okay. So what we had to do is just take some and average it out. So this is what we did. And third one was something related to something called Manhattan distance. So Manhattan distance between your two data point is x1 minus y1 mod plus x2 minus y2 mod. Okay, is this clear, Professor Sandeep?
Thank you. Thank you.
Let's move to hierarchical clustering for a while. Okay, now in hierarchical clustering there are like two approaches that are taken, but like One is like initially you assume that only you have only one cluster, and you keep dividing this your data point in further down. So like if you look at you might recall your biology class from class 9th or 10th, where you had living organism being divided into plants and animals, and then further plants were divided and animals were divided into mammals, probably fish and those kind of things. Okay, amphibians and those kind of things. So here initially we had two clusters and those clusters being further divided. Okay, so this one was probably not covered in the course, and the second one that was covered was like initially you assume that every data point is a separate cluster. Okay, and then you combine 2 points if you think these points are very similar to each other, and you move up this way, and you end up coming with a cluster that has like your only one cluster at the top. Okay, so this is something called agglomerative hierarchical clustering, and this is what we are going to cover right now. Okay, so step one is to treat every data point as an individual cluster. Okay, second one is to find the similarity between every pair of points or cluster. Okay, why I'm saying cluster is okay, let's say you began with every data point being a cluster. Okay, now let's say these 2 points were close to each other in the first step, and then you assigned it as one cluster, and other points are now again different clusters. Now you need to find the similarity between this cluster and this cluster. So this cluster has now 2 points and this has 1 point. So you need to find the similarity between every pair of cluster and the merge cluster that are nearest to each other. Okay, like whichever two are nearest to each other, you merge it in the next step. Repeat step 2 and 3 until you get one cluster. Okay. Now I'll just draw an dendrogram or an example how this is done. Let's say you have 4 points. In the first step, you found that your middle ones are similar to each other. So this is step 1. I should have. Okay. And in the next step, you found that your this point and this point are very similar. Okay. And in the next step, you probably found your this point and this point are similar. So this is a like hierarchy that you drew. Okay. So this is something called as a dendrogram that you obtain based on this similarity. This is called dendrogram. Okay, this is how you obtain it. Now, what you can do is based on your application, or you can use something like elbow method also. You can cut this thing at certain point. Let's say you cut it over here. Okay, to obtain a specific number of clusters. So if you cut here, how many clusters you would get? You would get 2 clusters. So what points would fall into this cluster? So this cluster, this yellow one, all these 3 points would fall into this yellow cluster. And in the other one, there would be only 1 point. Another thing is you could have cut this over here also. Then you would have got 3 clusters. Or initially, if you did cut here, then you would have got 4 clusters. Okay. So this is how this your agglomerative hierarchical clustering works. So example is like this. This is your dendrogram given to you. So it is asking like if they cut at y is equal to 2, how many clusters you would obtain. So as I mentioned, you will get 2 clusters. So if you would have cut over here, you would have got 3. Here you would have got 1, 2, 3, 4. Here you would have again increased 1, 5. Here you would have increased 6. And yeah, this is the maximum number you could have got. So this is how it works. Again, you can use the domain expertise, or the something like elbow method also can be used here also to decide upon the number of clusters. Okay. Now, like whatever we mentioned above, so we knew how to find similarity between points. Okay. So similarity between points would have been this Euclidean distance or Minkowski distance or those kind of things. How do we find the similarity between clusters now? That's one thing that need to be answered. So there are several ways that have been covered in the course. So first is a single link cluster. What is a single link cluster? If you have two clusters available with you, you look at the points which are closest to each other across clusters. So this point and this point are closest across, like if you look across the cluster. So you take the distance between these 2 points and you assign like the distance between these 2 points as distance between these two clusters. Okay. So this is how, like if you have two sets A and B, mathematically also distance between two sets A and B is minimum of uh, distance between A comma B, where your A belongs to A and B belongs to B. So this is on the same principle that you take the minimum distance that is possible across this set. The second one is this complete link principle. And in this, what happens is you take the points which are at a maximum distance apart. So you take distance to be maximum of distance AB, where your A belongs to A and B belongs to B. Okay. Third one is something called centroid method. So what you do is you take distance between centroids of both the clusters. So you have this cluster, you have this cluster, you take the average, yes, take the sum and average it out, and then you find centroid out of it, find centroid out of it, and then you take the distance between these two centroids. Last one is something called average link. What happens in average link is, I'll just give you first this one. So like for every, let's say there are two clusters. Okay. Then you take a similarity between every pair. You pick 1 point from here, you pick 1 point from here. You find out its similarity. Okay. And for every pair you have find its similarity and then sum it up and average it out. So this is one way of average linking. Another way is you combine these two things. Okay. So if these are your two clusters, you combine these two things. And then you find the similarity between every pair possible over here. Okay. So this is your C1 union Ci union Cj. And then you take a similarity between every pair of points. Okay. And then you average it out by number of pairs possible. So these are some of the techniques that you can use to find distance between your like clusters. Anything that you want to ask?
Sir, which one is like mostly used in practical scenarios?
See, what I feel is this single link would be sort of most used one. Even this centroid one is pretty good. Okay, but again, like these things vary a lot from your application to application. Like this can be a very naive answer that it varies from application to application. But if you look at this area of machine learning or these things, uh, things do vary a lot based on application to application.
Okay, so is it dependent on some type of sim data also? Like
Yeah.
application means like the data would be different for different applications, right?
Yes, yes, yes. That's what I meant. Like where you want to use the output that you have, or like what kind of data you have, it would definitely depend on that also.
Okay, thanks, sir.
So this is what I had in mind to cover today. So this is probably the last time we are meeting.